Super. Thank you so much. Thank you for that introduction, and thank you for the invitation to come here and speak. It's very welcome. I've actually been here before, about 10 years ago, when I was at the Geological Survey for Denmark and Greenland. I came and said something about, a little bit about resources or metals and minerals specifically as well, but also something about the Greenland geology, which I will not be touching on today. Instead, I will, as Tina said, I'll say a little bit about BGS, just so you know what kind of organization is BGS. And it is, of course, because I'm hoping that there's some students here that are going to come work with us in the future. So I'm hoping to get some of you excited about the role of BGS. But I'll go through that pretty quickly and turn to mineral criticality, which is something that everyone is talking about right now and everyone is excited about. And it's becoming a big agenda for a lot of organizations that do research and into minerals and metals, but also for government and for a lot of companies who are now finally taking this this topic seriously. So I'll talk a little bit about that as well. But first, BGS. So this is the sort of the speed dating profile. 5 slides about BGS, or maybe 6. So BGS, we like to say that we are world-leading geological survey. I'm not exactly sure what that means, but it's good. And what we basically are is a global geoscience organization. We are focused on what we call public good science. So it's really science for society, a science for the public good. And that's for government, and we do research to understand the earth and environmental processes. We are the UK premier provider of objective and authoritative geoscientific advice, information and knowledge to help society use its natural resources responsibly, to manage environmental change and be resilient to environmental hazards. And I'll touch briefly on that again in a later slide. We are the oldest geological survey in the world. We were founded back in 1835, and we have a staff around 600 and a turnover of about 55 million. And quite importantly, and this is actually the reason I put up this slide, because it's important to understand where we sit in the sort of research ecosystem or landscape, if you will. We are part of UKRI, and we are part of NERC, so the National Environment Research Council, and we sit as one of 6 research centers affiliated with NERC, and one of the 2 research centers that are fully owned by NERC, as NERC would put it. And those 2 research centers, of course, is BAS, the British Antarctic Survey, and BGS, the British Geological Survey. And I'll talk a little bit about some of the things that sets us perhaps apart from other research organizations as well. So this is actually a little bit sort of breaking news, because there's an updated mission statement that will be launched with our new strategy in a month's time. It hasn't changed dramatically since the last one, but it helps explain again what we do. Our vision is to be a leading and trusted provider of geological data and knowledge to meet societal needs for a sustainable future. Mission, to use our knowledge of geology to address societal challenges. We generate data, information, and expertise through observation, analysis, and characterization of the earth and geological processes, working at a local, regional, national, and global scale. So that's the sort of the spatial scale, but also monitoring at multiple temporal scales, from real time to multi-decadal. And that's actually one of the things that is typical for these research centers, that we get these kind of jobs where it's about collecting data for 50 years so that we can see long-term trends and making that data available to research organizations across the globe. And then very, very important, we are independent and impartial, because we have such a big role to play in providing data for society. We are a government advisor, if you will, and so we have to be able to be trusted for our advice. And our role is described in more detail in an MOU with NERC that was authored about 5 years ago or 6 years ago. And that role describes basically what that public good science looks like. What is it we're supposed to do that's unique to BGS? And it doesn't mean that some of this doesn't happen elsewhere, but this is really why we exist on this planet. And again, at the very top, we provide impartial and independent geoscientific advice. What I like to translate this to basically is that if if government comes and asks us a question, and Greenpeace asks a question, and Shell asks a question, it's the same question, they will be getting the same answer because they're going to get the best possible answer we can deliver based on the data that we have and the knowledge that we have with it. We provide a national repository for data and knowledge for geoscience in the UK. This is both in terms of rocks, but also in terms of data. We develop services to enable government, business, and the public to benefit from this national repository archive of data and knowledge. So that includes organizations like yours. Lots and lots of university students and staff come to BGS to look at our cores, to look at our rocks, to retrieve some of our data. We provide analytical facilities, including observatory networks in support of earth science research and government needs. It's everything ranging from geochemistry labs to seismic observatories and monitoring space weather. We deliver UK leadership and make our skills, expertise, and knowledge available globally. So this is really about our international work and providing that sort of UK leadership in the international scene of geoscience into public good. And we undertake research and development in pursuit of these aims. So that is sort of the one that it's hugely overlapping with universities, because to be able to do all the other things, we actually need to have a certain level of knowledge and skill, and that has to be current. So we engage in research projects alongside universities, alongside European partners and others to make sure that we can deliver on these things. And this is how we organize. That's actually our previous strategy. It's called Gateway to Earth. And we organize sort of like this with three, if you look at the dark blue here, three main, we call them challenge areas, and we probably should call them solution areas. But basically, it is where we think that our geoscience is going to help provide solutions to societal challenges in the overarching areas of decarbonization and resource management, environmental change, adaptation and resilience, and multi-hazards and resilience. And it won't surprise you, decarbonization and resource management is all about new energy technologies, it's about minerals, it's about all of the things that go into that. Environmental change, adaptation and resilience is about contamination, it's about groundwater, it's about overlapping with multi-hazards, it's about coastal stability and what happens in the shallow marine environment. And multi-hazards and resilience is about everything from flooding and landslides to volcanoes, earthquakes, and also the space weather that I briefly mentioned before. So most of our people are organized into these overarching challenge areas, but with a huge overlap because similar skills are needed in all of the areas to solve different sorts of problems. We also have an area that we call actually international and national geoscience now. So that's the work that we do on that local and regional and international scale. It's very much about mapping, about characterizing the subsurface and providing input into things like infrastructure decisions, that sort of thing. And then we have underpinning everything, we have our informatics and digital transformation. So we have about 100 people working with providing data services, maintaining our databases, providing ways of accessing the data and so forth. And then we have a operational area that's everything, estates, business development, public engagement, and all of those sorts of things. We have some metrics here, they're a little bit old, but I haven't gotten an updated figure yet. We have a little shy of 600 staff at the moment. Oh, sorry, this is not staff. Staff is the next one, I think. We have publications. We have 572 publications for this financial year. And these are publications that range from white papers and technical reports to peer-reviewed research articles. NERC has a data repository where they are making all of the research publications available that are coming out of NERC research. And basically, from that repository in this financial year, there were 322,557 downloads of BGS publications. And this is a number that actually makes me immensely proud because this is like 1,000 downloads a day, almost. Certainly for every working day, it's 1,000 downloads. So this is sort of something we use as a reality check on, are we doing the right stuff? Is what we do important to anyone? Does anyone need the kind of research and the kind of publications that we provide at BGS? And the answer to that's yes. And when you look at actually the top 20 downloads, 13 of those are BGS downloads. And for example, I think the top one actually, it's a characterization of the Mercer sandstone, or mudstone, which is very much a place that is looked at for being an aquifer, for being a potential storage area, for energy, for radioactive waste, for all sorts of other things. But that's the kind of, again, characterizing the subsurface is at the core of what we do. Financial statement, I don't want to go into detail with that, but quite importantly, we get about half of our funding outright from NERC to provide what they call national capability. And this is the sort of stuff that needs to be on a decadal scale. The seismic observatories, for example, the monitoring of groundwater quality every day for 50 years type stuff. There's a little bit boxed in here in green. Those are research infrastructures that we manage on behalf of NERC, but aren't really BGS business. This is the National Pool for Seismic Instruments, for example. That's based in Leicester. We do the administration of that, but have really nothing to do with it. So that's kind of flow-through money, but there's also some isotope laboratories and other things in there as well. But we get about 25 for this national capability. The other approximately 25 that we get from other sources, external sources. And those are shown down here. And as you can see, another 5 million of that's still NERC income. But these are the research grants. So this is stuff that we do together with organizations like yours. Then we get about 3.6 from government departments, something from other research council, other public sector. This is, for example, the National Waste Disposal for Radioactive Waste. UK private sector is 4 million. That's actually universities. So this is not private sector in the sense that you think it's other companies and others. It's actually when we work with universities. So those are research grants that are granted to universities and where we are partner in. Foreign public sector and foreign private sector, again, universities, and EU is a bit of chunk of money here. And then finally up here, we have a little bit of sales. So this is some of our data products and a little bit of other external incomes that's renting a couple of our offices out to others. So the important thing is to see that almost everything here is public funding. And that is really important because, again, we are a public good organization. And so we're not out there to compete with organizations that have a different remit, that are trying to make money, trying to be consultants, for example. We are there to provide public good. So a lot of our external funding actually comes down directly from government departments. Here was the staff one. It says 650. It's not entirely true. It's about 600 now. And this is where we're basically based. The headquarters in Keyworth, where I'm based. We have a couple of people in London at the Natural History Museum next door. But then our main offices are in Edinburgh, where we have 150 people. A small office in Wallingford, small office in Cardiff, and a small office in Belfast. And then the blue diamonds here are sort of places where we have only 1 or 2 staff, and there will be our observatories and our information point next door here in London. That's what I'm going to say about BGS, and it's probably already lasted longer than I want it and that you want it. But if you want to know more, especially students, if you want to know more about what we do at BGS, and specifically something about what actually goes into studying hazards and studying the environment, you're very welcome to reach out to me, and I can tell you more. I'm now going to switch to mineral criticality, very hot topic, and something that I'm personally quite passionate about. And again, I'll talk a little bit about what actually is criticality and how to perhaps think about it, and what's actually the problem with criticality and what might we do to try to solve it. And when we talk about minerals, it is, and again, I'm almost certainly preaching to the choir here, so I'm not going to spend a lot of time on this, but almost everything that we surround ourselves with in society is dug out of the ground at some point in time. It is ranging from the gravel under the roads, to the infrastructure, the transport, the houses, the energy technologies. You can see there's a wind turbine sitting somewhere in the background, and here you can see the minerals that go into all of those things. So a lot of things that we surround ourselves with is actually dug out of the ground. That's, of course, why it's even interesting to start talking about this. It's underpinning our lifestyle and our livelihoods. And if we look at the energy transition, this is, I use this in different contexts. Today we're going to talk about minerals, but it's a really useful figure to think about why geology and geoscience is important when we talk about these things. Sometimes my title of this slide will be Everything Starts with a Rock. Because when you look at this figure here, you see all of those new energy technologies that we're interested in. You see compressed air, hydrogen storage, CCS. You see mapping offshore to site for wind farms. Where do we actually put them? Where are they going to be stable? You see solar panels, deep and shallow geothermal. You see wind turbines on the on shore. You see more carbon capture and storage over here, storage of nuclear waste, as I mentioned before, and mining. For, in this particular case, we have a lithium battery on here, but it could also actually just be the gravel to put under our roads. So everything, every one of these solutions that we need for the energy transition and that we need for environmental sustainability in how we carry on our lives, every single one starts with understanding the subsurface and being able to characterize the subsurface. And we tend to think about this as engineering problems, and then maybe there's some engineers in this room too, which is great. And they are engineering problems, but they start with the rock. They start with actually being able to characterize what that rock looks like. And I'll zoom in, of course, on the mining now, because we'll talk a little bit about what are the metals and minerals that we need for actually all of these technologies as well. First of all, what's criticality? And again, everyone has an opinion about this right now. Everyone wants to own this agenda. And it's almost like, you know, I go to the hairdresser and she will ask me about, so what's up with this mineral criticality? You know, everyone has heard about it. Everyone's seeing it on the news. But what does it actually mean? And it's used very loosely, and that is one of the issues with it, because it's used as meaning important. It's very critical for blah, blah, blah. So we use it in day-to-day speech all the time, but critical actually has a definition, and it has many definitions actually, but importantly, it combines importance with vulnerability to supply. Those are the very two important axes, and you can define those slightly differently. It can take into account environmental or ethical issues as well, and it is typically looked at from some kind of viewpoint. We can't really talk about criticality for the globe, because when you look across the globe on average, there's probably enough of everything, and I'll return to that. But you can talk about criticality for a country. You can talk about criticality for a sector, and even a company that wants to produce something. What is it that's very important to what they do that there's a real risk that they can't get supplies of? That is what critical means. So it'll plot up here, most critical, when it's both important and there is a real supply risk. And when we look at the energy transition and different energy technologies, this here is from the World Bank study back from 2008. And basically you have different technologies up here. I don't know if you can read it. It says wind, solar, more solar, hydro, geothermal, energy storage, nuclear, coal, and so forth at the top. And then at the y-axis here, you have different metals or minerals. And basically you have a colored square wherever that mineral is needed in an energy technology. And what you can see, for example, is look at copper sitting up here, number 4 from the top. You need copper for every single one of them, obviously, because you need copper to transport your energy from wherever you create it to wherever you need it. So it doesn't matter what energy form we are using, we're going to need copper. If you look below, you have graphite, and you see graphite's only needed in energy storage, so pretty much only in batteries. And the same is true for something like lithium sitting down here. But again, there's sort of a variety of different metals being needed for different technologies. If you look at a estimation of how much of this might we need extra just because of the new energy that we want in the next couple of decades, so looking out to 2050, what you see here is percentage increase based on these energy technologies. And you have number 1 here is graphite, number 2 is lithium, number 3 is cobalt, and it's above 400%. So 4 times as much as we're using today. And those are the battery materials that we really pretty much only need for one thing. But then again, just like the copper, when it comes down to it, it actually doesn't matter what energy technology we're using. We're going to need to be able to store that energy, and we're going to be able to retrieve it when we need it. And that actually means that battery technologies is also going to be utilized across the board and end up being very important. And the other metals, of course, a little bit less. But we know there's going to be almost certainly a surge in demand here. There are different estimates of this that vary a bit, but all of the estimates arrive at the same conclusion. Demand is going to go up. And this here is a sort of foresight report from the EU from 2020. Many of the same elements and a few extras on here, but basically looking at what are the technologies that the different metals go into, and what are the sectors to which they are very important. And this is then sort of classifying the degree of criticality, if you will, predicted into the future for these different elements. And as you can see here, very highly critical. They have the rare earths that my hairdresser wants to know about all the time. Everyone talks about the rare earths. It's a fantastic example of something that's critical. But you also see on here high, you have magnesium, niobium, germanium, you have moderate, you have low, and actually quite interesting, if you look in the low, you have lithium, which is one of the ones where demand's going to go up hugely, and very low, you actually have copper. And this is really interesting because, again, you go out and talk about criticality to people, and they say, oh, copper is very critical, and lithium, super duper critical. It's not actually super duper critical. It's super duper important. And that's, again, the distinction that we have to make. It is absolutely very important, but right now, it looks like the copper industry will be able to actually match the demand, more or less. So we're not really afraid of a big supply risk, acknowledging that there's going to be an increase in demand, for sure, for copper and for lithium. So again, an important difference. The UK government has sort of entered into this space. My battery has died, Tina, so you have to tell me when on my watch, when I need to wrap up, which is hopefully a long ways off into the future. UK government has entered into the space, and starting actually with this report that came out in October 2021 that is called Build Back Greener. It's a very long report, and on page 258, I think it is, they talk about minerals, and they actually make some commitments of what they're going to do about minerals to reach net zero. And they say, we'll establish an expert committee to help us develop a critical mineral strategy. We will establish a UK Critical Minerals Intelligence Center, and we will publish a critical raw materials list for the UK, looking at that landscape with a UK lens. And they've done all of these things, and I'll talk a little bit about that when we get a little bit further. But first, I want to talk a little bit about what we might do about getting these different things. We first look at the critical minerals list. I will say a little bit about that first, or the Critical Minerals Center. That was established in April of last year, and it is based at BGS, actually. So all the work is not based at BGS, but the actual center is sort of is based there, and with the idea of reaching out to other experts, including them in different studies. And basically what the center is supposed to do for government is to map global critical mineral supply chains, track stocks and flow, monitor market dynamics, and understand associated economic, geopolitical, environmental, and ethical risks and opportunities. And there's been some deliverables coming out already. Importantly, that critical minerals list that the government promised to deliver, and also a supply-demand forecast to 2030 for some of the battery raw materials, looking at it again with the UK lens of saying, if we're going to have battery production in the UK, what would it take? And that report is always also out. And there's a couple of other things, and you can find all of that on the website. And if you look at the criticality assessment that we did, basically these two main things, the supply risk and how important is it, we used 9 different parameters to try to assess that. And so for the supply risk, we look at production concentration, companion metal fraction. So is it being mined for that metal, or is it a byproduct? And recycling rate. And economic vulnerability, that is sort of really the importance. How bad would it be for the UK if we couldn't get this? So that is how important it is. Production evolution, price volatility, substitutability, global trade concentration, UK import reliance, and UK gross value added contribution. So each of these 9 parameters we have looked at, not me personally, but the great team at BGS has looked at this and tried to give a score to every single one and have come up with what we think is important for the UK. And it looks like this, and this was done actually towards the end of last year, and it's currently being revised, because that's the interesting thing about criticality. Because it has that supply risk portion to it, it's very dynamic. It could change overnight. We could have a war break out somewhere in Europe, for example, after this assessment was made, which is actually what happened. And that might change how we think about things like palladium and nickel and other things that Russia is a big producer of. But basically what you can see here is lithium just made the cut into the criticality space here. But these are the ones that were assessed to be critical to the UK. And in this context here, the solid versus open symbols signifies how confident we are about the data for that particular metal or mineral. And you can read more about that in the report if you're interested, but basically these are the metals that are critical to the UK. And now I want to switch into this thing, how are we going to get them? What are we going to do about this? What are we going to do in the UK? What are we going to do globally? And we pretty much have three options. We can manage without it, and you will hear that. You'll hear people say we should just be more responsible in our consumption, and we should just not all drive a car, and we should not all do all these things, and that way we'll drive demand down, and that will solve the problem for us. And then you have second option, we can recycle it. So I sort of move towards a circular economy, and we can just all empty our drawers for gadgets, and we'll mine that, and we'll be good to go. And the third one, of course, is that we're gonna mine it. We're gonna dig it out of the ground. And so I'm gonna just briefly touch, not that briefly actually, I have lots and lots of time left. So I'm gonna touch on those three. Can we manage without these metals and minerals? Is that actually a viable option for clean energy? And it's, you know, it's possible that I could probably consume more sustainably, and it's possible that every single person in this room probably could use a little bit less and be fine. But when you look globally, and we have to look globally when we have to address these issues, we have 940 million people in the world that do not have access to electricity. We have 3 billion, that's 40% of the world population, are cooking over an open fire, which is not a healthy thing to be doing. Can they do with less? Maybe. Per capita, electricity consumption varies more than 100-fold across the world, and per capita energy consumption varies more than 10-fold across the world, not surprisingly. And again, yes, we could probably do a little bit less, but can? We probably are at the high end of that range. Can the ones at the other end actually just do with less? And not surprisingly, energy access is strongly related to income, and probably income per country in that sense. So if we're serious about this, if we're serious about no poverty, good health and well-being, affordable and clean energy, reduced inequalities, even gender equality, I know who the 3 billion cooking over an open fire probably are. Climate action, all of those things. We don't need less energy in the world, actually. We need access to energy for more people. So using less as a global solution is probably not the right one. Maybe having more sort of equal access to these things is part of the solution. I'm not going to say any more about that. I'll move to recycling, which is another favorite, because that's very green. We can all get behind recycling and circular economy. And in May, not 2 days ago, but in May, there was a big story on BBC saying that scientists say mine e-waste, not the earth. And it happened on a Sunday morning, actually. The story broke, and I'm sitting there drinking my coffee, doing my Wordle, and I hear BBC News talking about minerals and mining. And I'm like, oh, what is that? And I go online, and I find this article that basically says we should stop mining because we're running out. So instead, we should start recycling. So how realistic is that option? Well, again, it's very green. We all like it. And if you Google circular economy and hit images, you get 1,000 things that look like this. This is an actual screenshot of me doing just that. And just looking at partially some of the results that you get. And you get figures that look like this. So there's as many ways of thinking about this as ways there are of thinking about critical minerals. Everyone have their own definition. But common to them, if you look at them, they tend to be green. People like using the color green for representing these things because it makes us feel really good about it. And they also like to do, and this is a very simple one, they like to do these closed loops because that's the idea, right? We don't have to mine because we're running out, and instead we'll just recycle forever and ever. And the thing about that is that there's several issues with that. It's obviously a good thing to recycle, but when we look at what are the raw materials that we're actually using, we get this trend here that whenever we get new technologies, we start using new metals. So 50 years ago, for example, we didn't really use rare earths. I mean, we didn't use them. They aren't actually really there in the stock, if you will. They're not available necessarily for us to mine. We pretty much need the entire periodic table with the amount of advancement that we've had technologically. And we didn't used to do that. So there's some things, and if you look at, for example, at things like copper, we always used copper, for a long time anyway. That is actually available for us to recycle and has been for a couple of 100 years. And I'll return a little bit to the time scale of recycling, because that's part of the problem or part of the solution here. And this figure, I love repetition, is going to remind me about that, because very importantly, as long as I'm driving my car, you can't recycle it. So as long as we're using something, it's in the stock and it's not necessarily available to recycle. And another aspect of circular economy, of course, is that we want to build things to last. We want to build things to last for a long time, and we want to be able to repair them rather than throw them away. That's a very core concept of circular economy. And so if I build a wind turbine that's going to sit there for 50 years, it's a good thing. It's going to be 50 years before I can recycle that neodymium. And that is an important thing to remember. It doesn't mean that we shouldn't assign that wind turbine to be recycled in 50 years' time. Absolutely, we should. But it's not going to be available to us to recycle tomorrow or even in the next decade. And we need to build windmills in the next decade. We need neodymium right now if we're serious about net zero by, just around the corner. We need to do this now. As long as we're using it, we can't actually recycle it. And thirdly, more repetition. When you have an increase in demand, there's some real simple math that enters into this. If you need twice as much next year as you did this year, that's a very, very big number and not realistic. But in principle, if you need twice as much next year as you had this year, you're not going to be able to recycle what you're using this year next year. It would only cover half. And this figure actually sort of shows this. It's a little bit lame, but it's very important actually, because it has it's basically assuming an 8% annual demand increase, not double, but just 8%, which is actually also a lot. But still, it's kind of okay with some of the things we're talking about here. So how much can be covered by recycling if, in the pink case, let's look at that one first, we can actually recycle 100%. That is extracting every atom of every metal in this thing and getting it back into something useful. 100%. If we can recycle 100%, we use it for 1 year, next year we extract 100%, but we need 8% more because we have an 8%. It will only cover 92% of what we need. That's pretty simple. The interesting thing is that there's sort of several things here, is that we're not good at extracting 100%. There are exceptions to that. Copper, we're good. Aluminium, we're good. Steel, we're good. Close to 100%. High. Very good. But at most other things, we're not actually that good. So we have to look at some of the other colored curves. And then, of course, there's the x-axis. What's up with that? And this is the thing. When scientists go out and say, don't mind the Earth, because we're running out, we all have this picture in our heads of our waste. And for good reason, because we have enormous amounts of waste lying around. There's no question about it. We're all guilty of having stuff at home in our drawers too. And if we all went home and we emptied that out, and emptied out our garage and all the other stuff, and we piled it all up, there would probably be a lot of metal there. And we could probably get a lot out of that. And we might even be able to get enough to meet an annual increase for a year, or 2 years, or for 3 years maybe, but then we're out. Then the drawers are empty, the garage is empty, everything's empty. So actually, when we think about making recycling sustainable, we have to think about an annual consumption of this. So you can actually, for every 1 year where you need metals, you can only recycle 1 year, because otherwise you cannibalize your stock and you end up with nothing in the stock. So you could do it for a little while, and we probably should do it. There's good reason to do some urban mining and get rid of some of all that waste, valorize it, but it's not going to be sustainable in a increasing demand kind of scenario. And this is just to show, this is unfortunately an old figure. I've been looking for an updated version, but I haven't been able to find it. But this is a periodic table that basically shows you how good we are at recycling. So which of those colored curves you should look at. And again, there's some things where we're good. The blue here is above 50%. It's copper, zinc, nickel, iron, lots of things that we actually are good at recycling. And then there are other things, not so much. The rare earths that everyone's talking about, including my hairdresser. Less than 1%. Are we able to recycle? Are we currently recycling? And some of this has to do with the ability to do it, because it's hard to unmix. I know we have metallurgists in the room here. Unmixing of metals is not a trivial thing. It's not trivial when you do it from a rock, extracting it from there, but it's certainly also not trivial when you're unmixing it from here, because it is mixed for optimal performance with this gadget. So that's the reality of the recycling. That gets us to mining, and I'm actually not necessarily going to say that much about mining. Many people here know more about mining than I do, but we do have to look at this. It's brown and it's dirty, has a bad reputation, partly for good reason, but it's time to try to change that reputation, because we probably do need it. And are we running out? Well, this is a USGS screen dump from July of this year. It was inspired by the BBC news piece, and it's actually screening for, there's more elements on here, but my legend, I chose 4 of the things that the scientists in the BBC study said that we were running out of. Notably, the scientists in the BBC study, I'm sure are very, very good scientists, but they're not earth scientists. It was, I think, the Royal Society of Chemists that published that study. But basically, they have, for example, gallium on their we're running out list. And if you look at that color there, that purple there, and you look at gallium, I mean, these are just occurrences and deposits. They're not necessarily viable, but we're not actually geologically running out. And that is a very important thing about criticality, that there's not one single case of a critical metal on any list, the EU list, the US list, the UK list, any of these lists. It's not one single thing that's on there because of lack of geological availability. It's always about something else. And that's a very important thing to understand. Another thing about mining, and this is just sort of to provoke some thinking on your part. This is all metals and ores that are mined. You can't see my top line there, but we'll manage. That's mined in the world. This is BGS data. This is part of what we do. It's part of our national capability. We sit down and chew through databases from all over the world and put this data together every year. And what you see here is that this column is everything that's mined in the whole world. And what you can see is tonnage, it's not value, but what you can see is that it's almost all iron. Almost everything that we mine is actually iron. The bit that isn't is represented by this rectangle up here. And if we blow that up and say, what's in that? What is it we mine then that isn't iron? Well, you see it here. It's aluminium, it's manganese, it's chromium, it's copper, it's zinc, it's titanium, a few other things up here. And here, that little top right-hand corner square that's gray is technology and precious metals. If we blow that up, let's look at that. Let's look at what that does. It looks like this. There's some molybdenum, some tin, some lithium is sitting here. Critical metal. And you hear these things in the newspapers. It's like, we're gonna need so much mining to, for the green transition. It's crazy. We're gonna need so much mining. We are gonna see an increase in demand of several 100%, yes, but it's not gonna compare to this. At the end of the day, it's not actually that much mining that we're gonna need. And that's one of the really interesting things about this, because it's not big. And maybe that is one of the issues about criticality. Tina and I talked a little bit about this before we came in here, that there's something another very interesting thing on this thing here is up here, that tiny, tiny elongate gray area here is gold, 3,000. Half of everything that gets invested into mining and into exploration for metals is invested into gold. So there's a huge disconnect with what we actually think is important and what is actually being invested in. And we're not seeing much investment into lithium and into rare earths because it's complicated. It's takeoff agreements. It isn't traded. Gold is traded easily. And that's one of the reasons it's a very safe investment, or a relatively safe investment compared to some of these things. So there's something about the business models for how we do that I find very intriguing. And I know that there are people at this school that think about a lot, and I think you should think a lot more about that, because I think that part of the solution is probably in understanding why this picture looks like this, and why half of everything we invest into any of all of this is invested into mining for gold, which isn't terribly useful, to be honest. It is a little bit useful, but it's not critical by any list or any standard. And that gets me to, I'm getting close to the solution now, getting close to the end. So what does it all look like? What does supply chain look like? What does the solution look like? Circular economy, how do we think about this? What is it we need to do as a society? And I like to, my version of the figure, if you Google circular economy, looks like this. It is very important to understand that you always, always, always need to put things into the loop. In a scenario where you have a decreasing demand, something that we're going to stop using, it is possible that you can just recycle and you'll be fine. You'll get enough from that. But some point in time, it was dug out of the ground and it was put into the loop, or it wouldn't be there for us to recycle. So it's very important that we talk honestly about this, and we talk honestly about that there is a environmental footprint and social footprint from the exploration and from the mining, and there's waste already here. Most of these circular economy ones are, nothing feeds into them and there's no waste, because that's the whole idea. But actually there's waste, and there's waste everywhere, starting with the mining waste. So doing this well is going to be important, regardless. But also doing all the other stuff well, when it then comes into this loop, the processing around it, the waste that we have from that, raw materials, we call both these and these raw materials, but these are the actual metals that you can put into products. And then these guys, which I think have been very important, probably very critically important to the solution. So these are the ones that design our gadgets and sell them for money. So they are the OEMs. They're the Apples, the Audis, the Siemens. What if they were interested in where the metals came from? And what if they were interested in recycling them when they were done with them? That would be a very, very good way of trying to start closing the loop on some of these things. And then, of course, you have us down here, the end user, and us not necessarily getting things out of the drawer and bringing things back into the loop. So that is how I think we need to start thinking about these things. And one way of doing that, again, if we want to engage these guys who are used to, if you go back 20 years, they just bought metals off the shelf. They didn't care where they came from. As long as they didn't have to pay more for their metals than their competitor, whatever. But they're starting to care, and that's a really good thing. And one way perhaps is to make them care, to demand of them that they care, and they actually take responsibility for that. And there's several initiatives that try to do this. And this is a very messy slide, but it's just really meant to show that things like standards, certifications, and best practices are being developed. Probably too many are being developed in parallel right now, and we'll see what crystallizes out as the sustainable ones. But it's a little bit like think about fair trade coffee. It's about, can we certify that something has actually been done in the best possible way? And again, it's important to acknowledge that best possible way doesn't mean that there's no environmental footprint, but it means owning that environmental footprint and assessing it and managing it and thinking about it. It's a little bit like farming. Farming has a huge environmental imprint, but no one says we shouldn't farm, but we talk about how we should farm. It's a little bit the same we need to do here. And I also put on here, and this is for Satinder, we have here the UNFC system looking at resources, which is sort of introducing some different variables. Traditionally, when you look at metals, for sure, You've basically looked at economic viability, and you've done York assessments or other kind of certified assessments that are meant to attract investment. So it's been a business certification that it is a sound and financially viable business. And what the UNFC does, so the UN Framework Classification of Resources, is it adds in dimensions of social and environmental impacts and how big or little that is. And the idea, of course, being that you can use this to make decisions about resource management at a high level, at government level, at regional level, instead of just at a financial level. Ideally trying to compare apples and oranges and sort of say, is this, because one of the really important things here is actually that when you decide not to open a mine somewhere, you are in essence deciding to open it somewhere else. And that is what has happened over the last many, many decades. Like, we don't want it, it's dirty. Let's put it in Africa. It's going to be much better for the environment. Is it? Probably not. How am I doing on time, Tina? I have another 5 minutes. I'm just going to run through this because there is the UK critical mineral strategy, and it's 3 summary slides. What the UK actually going to try to do, and this is important for all of us, they basically have a strategy that has 3 points, and they spell ACE. First one is accelerate the UK's domestic capabilities, and there are 4 points. It's a 10-point plan. Maximize what the UK can produce domestically, so we're looking at, can we actually mine some things in the UK? Rebuild skills in mining and minerals. This is really good news to everyone in this room, I hope. This is going to be something that there will probably be money behind. Carry out cutting-edge research and development to solve the challenges of critical mineral supply. Also good news in this room. And make better use of what we have by accelerating a circular economy of critical minerals in the UK. All good stuff. The second one, the C, is collaborate. And that is actually acknowledging that we cannot solve this nationally. We have to solve it globally. Diversify supply across the world so we become more resilient, support UK companies to participate overseas, and develop our diplomatic, trading, and development relationships around the world. Another part of the solution. And the third part of the solution, enhance, the E in ACE, enhance the international markets. It's a little bit connected to the other one. Boost global environment, social, and governance performance, ESG. Reduce vulnerability to disruption by leveling up the playing field for responsible businesses. Develop well-functioning and transparent markets to improved data and traceability. That's what I just touched on. And champion London as the world's capital for responsible finance for critical minerals. Also very important. With that, I am actually at my last slide. That's another repetition on here, but just sort of saying, what is it actually we're going to try to do? We're going to do all of these things. We're not exactly going to manage without them, but we're going to be more sustainable and have more equality in how we consume. We should aim for that. We need to recycle and move towards circular economy. We need to mine, and we need to, as before, we need to understand resources from the geology to the supply chains to be able to actually deliver on all of this. And then I'm done.